you very much. First of all, I would like to say I'm really very happy to be here. This is my second visit, and thank you so much for the invitation. Okay, the topic is constraint qualification and existence of multipliers for non-convex infinite constraint optimization problem in Banach space. This is a joint work with my students, Krzysztof Leśniewski and Krzysztof Rutkowski, and essentially and the problem we consider is an infinite programming problem. So essentially, the most important thing here is the definition of the feasible set, which is given as a system of an infinite number of equalities and inequalities, and the total number of everything is at most countable. And in fact, the idea which is behind our approach is that, in fact, what we can try to have a look at this problem as a representation of some more general thing with respect to some particular Schauder basis. So essentially, this problem falls within a bit more general formulation where the number of inequality constraints and also equality can be uncountable in general. This set T can be assumed to be compact or non-compact. This goes back to some papers of Morduchowicz and Gia. Essentially, this falls within the approaches which are trying to extend Margasarian-Fromowitz. And what is typical for this approach is that essentially the derivative of the equality constraint at the point in question is surjective. This is also one point which we would like to avoid. And another approach which is more general, this is in operator form. Everything is so essentially this is the second line of reasoning, and it leads to some asymptotic KKT conditions or regularity which allows to deduce the existence of Lagrange multipliers. So in some sense we will put together the two with the help of a Schauder basis. So I'm sorry for this. I will give a very short account, essentially mainly only the definition. So what we are trying to do, we are trying to move with some typical reasoning, finite dimensional reasoning, where the basis is something very natural, to Schauder basis, and this is why we are considering the only countable number of constraints. So, apart from the classical definition, what is the most important construction is the construction of a certain cone. A cone which is related directly to the Schauder basis, which is chosen for the consideration. So it is defined in a very natural way. These things, these are coefficients. So essentially, the cone are these elements of our space capital F, such that the coefficients in this basis satisfies a certain number of equality and inequality constraints. Here, the indices sets are the same as above. And this set is closed convex, which is okay, but has no interior points, and this is called a basis cone. So So essentially, with the help of this cone, we can represent our problem, our original problem, in the operator form by introducing this function capital G and considering our function as a coefficient of the representation of our function capital G in a given basis. This is orthonormal system related to, okay, essentially these are coefficients in this basis. And with the help of this, our set capital F is as previously, and in the same way we have the representation in the operator form. So this is this way. The reverse way is much more difficult. So if we start from the operator form, so we have g of x in con k, so and con k, for instance, is a natural cone in some space, so it is almost always impossible to reach this form because natural ordering cones are in principle not representable in the Schauder basis form. Yes, that there exists some nice example related to this. Okay, so I would like to speak about some general aims. Next, I will define the basic constraint qualification, which is called constant rank. Maybe the name is not very happy because there exist already several other concepts with the same name. And the main tool which I will use is the rank theorem, and it has some important consequences. And also, this is a body condition, and finally we discuss existence of Lagrange multiplier. Okay, so the first aim is to ensure a body condition without, if possible, referring to surjectivity of the constraint map. And let me mention just very briefly that in the classical constraint qualification, one of which is Robinson constraint qualification. Essentially, if we consider only equality constraint, then Robinson is just means just the surjectivity operator. In the case of linear operator, this is like this. In the case of nonlinear equality constraint, this means that this is Freshe derivative is surjective. And also let me mention that, for instance, if we consider metric regularity, and if we assume that the operator is differentiable, Freshe differentiable, maybe C1, I don't remember exactly, this reduces, so metric regularity in the case of Freshe differentiable operator also reduces to the surjectivity of the derivative. So essentially, in some sense, the classical concept in a considered case reduce in some important situations to surjectivity of the derivative of the constraint map. Okay, so here there are just classical things. So Bouligand tangent cone is defined as usual, and also the linearized cone. And here our cone capital K is the one related to the to a given Schauder basis. Linearized cone as always, and what is possible within this approach is to define the active and inactive indices in the usual way. Okay, so here, continuing this reasoning, if we have our cone K defined, this cone related to base, I will call it basis cone, I think, what can be encountered in the literature, then we can easily calculate the tangent tangent to this cone, and also as for what concerns this linearized cone, we can assuming that our function is C1, we can provide some formulas for the linearized cone. Okay, now our main tool here is the rank theorem. I recall this theorem here because it seems to me that this is not very common in the context of constraint qualification to rely on this result, whereas this is one of the not that numerous theorem in nonlinear analysis which address directly the case when the derivative is not surjective. So the most important condition here is the one in blue, which means that the derivative restricted to this subspace capital E sub 1 is an isomorphism. What is E sub 1? So the kernel of the derivative is E sub 2, and this is the closed complement. Of course, here there is the general framework is that everything. I mean the image and the kernel admits closed complements. This is the main situation, and when these assumptions are satisfied, then we can find some diffeomorphism which acts like this. Okay, so this is our main tool. Next, I would like to present. This is one of the rare theorems when the existence of Lagrange multipliers is related to the rank theorem, and you see here this is essentially as in the rank theorem. So we assume some splittings of the underlying spaces, and what is more important is this assumption. F2 is a closed subspace which is complemented such that F1, so the image of of the space capital E under the derivative is complemented in F. And this is the condition which ensures the existence of the Lagrange multiplier. Let me mention that here this applies also to the situation where the image of the derivative at a given point is dense. Yes? So this is in some sense some extreme situation. Okay. So what can we do in a more general case? Now we define constant rank condition, which is, yes, and here, as I mentioned at the beginning, this terminology is sometimes a bit overused. So this is the general framework in the space of coefficients in a Schauder basis of a given element. So essentially, in this framework, there is a topological isomorphism between the space itself and the sequences of their coefficients in a given Schauder basis. Okay, so here is the first condition we are using. So essentially, the most important assumption is this assumption 10, which condition is this condition. So what is the situation? We start with a certain number of functions fi. This is this j sub 1. It could be infinite, but countable as always. And we can find a subset such that this acting on this subset the derivatives form a Schauder basis for this space. And moreover, there is a neighborhood. This is maintained in a certain neighborhood of the point in question. And yes, maybe an important observation is here that in fact, if everything happens on a finite set, then this reduces to the condition that the rank of the derivative is maintained in a neighborhood of a given point. So this is more or less that can be considered as a generalization. Now, this was for any function. Now, in the context of optimization problem, what is the most important? So here is, here is a constant rank condition. So essentially, we can repeat the point 1 and 2 as previously, and we add some technical conditions. These conditions are purely technical, and here you see that some properties of the Schauder basis enters into play, which is, well, I think we could expect these sort of assumptions here. So this is not very demanding. Okay, and what is important that this constant rank condition allows some functional dependence result. So if we start with our functions fi, and so to say non-basic functions can be represented as some functions of basic functions. This is how we can interpret this condition, and this is very important when we are investigating the tangent comp. Okay, and here is the main contribution of this research. So this is the concept of relaxed constant rank constraint qualification. Okay, so the term relaxed refers to this. So we are considering all the subsets, capital J, but only those which contain the equality constraints. This goes back, I think, to the quite an old idea. In my experience, I met this condition when working with Leonid Minchenko, who was probably a person who introduced some important contribution to this idea that in fact it is enough to consider only J which include the equality constraint. And the rest is more or less the same. So for all J we have this CRC plus. CRC is a constant rank condition. Plus means that we have this some additional technical conditions. So here this is rewritten. Okay. And this can be a bit simplified if the space capital E is reflexive. Okay, so this is we can remove some of these technical conditions are satisfied automatically. Okay, so what is our main result here? So the main result here that in fact this relaxed constraint qualification with some where plus means this technical things. If this holds, then Abadi constraint qualification holds, provided some condition 1 is satisfied. What is this condition 1? Condition 1 is condition say that in fact when we are when we are considering this sort of a point, so immediately you can guess that it appears in the context when we are calculating the tangent cone. So in some sense we can find a single epsilon 0 such that we are able to have this inequality for all I. And of course, the reason is that these sets are infinite. If they are finite, then this is automatically satisfied. And the similar condition appears, I think, also in the paper of Rutkowski and Gia. So each time we are fighting in some sense with this situation that we have an infinite number of constraints which should be satisfied at this point, so we need some uniformity here. Okay, now to close my talk, I would like to say that in fact this abadi condition is not enough to get the existence of Lagrange multipliers. And what is important in this context, I think this is also observed in this paper 6, that in fact what is important is this set. And this set must weakly star closed. So essentially, this set has some historical remarks can be given. Maybe this refers to some very old paper by Hurwitz, and which is published long ago, and also by Kurcyusz. The importance of this set is observed, and some properties about 20 years later have been observed. And also this convex right now in the context, in the same context, in fact. And we call this set a Hurwitz set. And as in this paper 6, we can show that this is more or less a general fact, that if we have abadi condition plus weak star closedness of the Hurwitz set, then the Lagrange multipliers exist. So I will not speak about this because this is more or less known. What I would like to observe that if we have only equality constraints, okay, this A1 is responsible for inequality constraints. So if we have only equality constraints, then this Hurwitz set is automatically weakly star closed, and we obtain the following theorem for the non-emptiness of the Lagrange multiplier set. And this, if probably you remember, the theorem I recall at the beginning by Blot, where in fact he was using the condition which is a bit different, but it is closely related to this one. So the theorem by Blot and this theorem are very close to each other. Okay, maybe some conclusions. First of all what I said until now depends upon basis. This is more or less clear. But also, what is maybe not that obvious depends upon the representation. If we have our feasible set, for instance, just equalities, so in some, and if we think about this capital H as, for instance, differential operator, yes? So in some cases, we can calculate the solution, calculate F, yes? In optimal control, when we have the dependence also upon boundary or initial condition, so we can calculate this F. And essentially, our constraint is no longer this, but just this. Yes. So and this makes a difference in our approach. Yes. So either this or this. And another thing is Gato differentiability. Everywhere I was using Fréchet. For Gato, first of all, we do not have rank theorem, at least to my knowledge. What we do have is Lusternik graphs. So there are some results by Urszula Ledzewicz where this essentially this problem is considered. Okay, so finally, when we are here in Erwin Schrödinger Center, so maybe it's an appropriate moment to speak about PDE here. Yes, here this capital H is a PDE, and of course I am not from PDE community, but I was interested in this condition in general. So essentially, there are not that numerous results concerning this, but there are some. So my approach I presented here when I was trying to be as general as possible in the context of non-surjectivity of the operators defining the feasible set. Maybe this can be overcome somehow by investigating surjectivity, for instance, of differential operators. Here there are, I think, quite an old result of Hormander, for some, of course, for some differential, I think, Euler-type differential operators. There are some results, also more recent by Paweł Domański. Okay, so this is more or less everything, and the presentation is based on the following paper. Here I mentioned this paper with Leonid Minchenko, which is not exactly the topic I discussed here, but essentially here there is this idea. So Minchenko idea is, first of all, to consider this relaxed, and next in the context or together with the rank theorem. So this is not that common in our community to use this rank theorem. This is why I recorded it here. And there are two papers. The first paper is devoted to the situation when, in fact, the indices are finite, so everything is much simpler. So rank of some subspaces is maintained in a neighborhood of a point in question. And this second point is an attempt to introduce or to use, so to say, to use Schauder basis in the context of infinite programming.